Alright, I hope you enjoyed that intro clip. I'm starting to make a little bit more full quality videos now with a little bit of an intro and a conclusion. This is the Unit 7 FRQ packet with the examples. Unit 7 is all about differential equations, and that includes slope fields, Euler's method, logistical growth models, all that kind of stuff. So this is number 6 from the 2018 test. This is the only question on this packet that has to do with slope fields. Usually in the past, slope fields have been about like sketching them or interpreting them on multiple choice questions and sketching them on the free response questions. For this problem, all that was required for this part was to sketch the solution curves. Okay, so one use of slope fields is that you can use a slope field, you can use the differential equation, which is the dy dx equation, to create the slope field. So you can kind of see a pattern, a wave pattern here in this coordinate plane here. The wave pattern allows us to figure out what is the solution curve at a particular point. A solution curve is the y equals curve. So you can kind of think of this equation as the f prime of x graph. And what we're trying to do is, since this derivative has both x and y in it, we're trying to use the slope field to get back to understand what is the original function, the solution curve, what does that look like? And this is your y equals curve. All right, so this is dy dx, this is just regular y. All right, so we're trying to understand what is y equals using a slope field here. So sketch the solution curve that passes through the point 0, 2. So here's 0, 2. The solution curve is the line that goes through 0, 2, and you can use the slope field to see what does that line look like. And if you look around the point, you notice that all these slopes are 0, so it's just a horizontal line there. That's the solution curve at that point. Then the solution curve for 1, 0 is over here. It goes to this coordinate here. Now over here, your slope, the little dash marks are different around this coordinate. It looks like something like this. It goes down, levels off, and then goes up the other way in the same direction, just in the opposite direction. So something like, trying to make it look symmetrical, something like that. So this is the other solution curve that goes through this coordinate here. So the differential equation gives us multiple solution curves depending on the coordinate that's that the line goes through. The next question is a more commonly asked question on free response questions. This has to do with separation of variables. This comes up very often. Separation of variables is all about moving the y's to one side and moving the x's to the other side of the equation. And this part C, tells us find the particular solution, meaning when it says particular solution, we want to find what's the y equals equation. And particular means we have to figure out what that plus c is. A plus c is general, but if you find a value for that c value, that's a particular solution. That's one specific curve, one specific line on the graph. So we're trying to figure out what's the y equals equation, and we could do that using separation of variables. Usually when you have a particular solution, you'll be given an initial condition right here. F of 2 is equal to 3. So let's first start by separating our variables for this differential equation. I want to move my x's to one side and my y's to the other side. So I'm going to leave dy here, and I'm going to move dx over here like this. So I had my dy stay on the left side. My dx, I moved it to the right side. Since x minus 1 is already something in terms of x, I'm going to leave it there. But y squared, I need to move it to the y side. So that I need to do that by dividing 1 over y squared. And I can just put a 1 back up in the numerator right here. So that's my first step, is to separate the variables. The next thing I want to do is I need to integrate both sides once I've separated the variables. So when I separate my variables and rewrite it like this fraction, what I can do actually is I can since it's a y squared, I'm going to write that as y to the power of -2. And I'm going to leave this the way it is. This is going to be a natural log because my x has an exponent of 1. If your x or y has an exponent of something other than 1, you'll need to rewrite the exponent so that it's like this. So I need to antiderive, so add 1 to the exponent and then divide by the new exponent. And then when I antiderive 1 over x minus 1, that's a natural log of x minus 1 plus c. So there's my general solution. It's not solved for y, but it's still a general solution. I'm going to take one more step to rewrite this side because I don't want to keep this negative exponent here. I'm going to move y down to the denominator. And since the entire since I have a -1 in the denominator, that's like making the entire thing a negative value. So I can just put that -1 right here, and that's okay. So -1 over y is equal to natural log of x minus 1 plus c. So now I want to find the particular solution by plugging in this coordinate 2, 3 into here, and then I can solve for the c value. So x is 2, y is 3. So -1/3 equals natural log of 2 minus 1 plus c. So now let's try to see if we can simplify this down a little bit. If you look on your study guide, natural log of 1 is equal to 0. So I can cancel that out, that's a 0. So that means c is equal to -1/3. So c is equal to -1/3. So now I can take this and I can rewrite my equation with that -1/3 in there. So my end goal is to write the y equals equation. Right now it's -1 over y. -1 over y is equal to natural log of x minus 1 minus 1/3 now instead of plus c. We figured out c is -1/3, so I re-put that into the equation now. And now I need to write this as a y equals equation. So if this is a fraction and y is in the denominator, and I flip this fraction, y is now in the numerator. If I flip this side, I have to flip this side. And I can put a 1 in the numerator here, and a natural log x minus 1 minus 1/3 over in the denominator here. So I flipped both of these fractions. You can kind of think of all of this over 1. So when I flip it, the 1 goes to the numerator and the natural log stuff goes down in the denominator. And I still also have this -1 that I didn't look at. When I flip this, the -1 goes down here, but I want to move it multiplied over here. So this becomes a negative right there. There is your particular solution. Your end goal with a particular solution is to get y equals stuff in terms of x. You don't want that c in there, that's why we solve for it. Alright, this is number 4 from the 2017 test. This is also a separation of variables problem, but it is also asking us to use that equation. Okay, so let me just identify where it's asking me to do that. It says, find an expression for g of t. That is meaning find the y equals equation. This is dg dt. It's asking us to find g of t. So I need to separate the variables here for this equation, integrate, solve for g. Then I need to use that equation to find what is the internal temperature of the potato at time t equals 3. Okay, so there's a lot of different things going on in here. Let's just first start at the basic differential equation and separate the variables. Let's just start there. So I'm going to have dg, I'll leave that on the left side, and I'll move dt over to the right side. And notice how everything over here is in terms of g. So I need to move all of that together. I can't separate it in I can't separate those terms inside of this parentheses here. I need to move them all this way. So what I'm going to do is I'm going to have 1 over that guy. G minus 27 to the 2/3. What I need to do here, though, is I need to rewrite this as a negative exponent. That's what I should have done. So in my next step, I'll kind of combine it with this step and just write this guy with a negative 2/3 exponent. G minus 27 to the negative 2/3. All right, there we go. Now we're good to go. I can still anti-derive this just like I said before. It's still a u substitution. G minus 27 is u. So we get G minus 27. I'm going to add 1 to my exponent, so that makes this a positive 1/3. And then I'm going to divide by 1/3. So if I divide by 1/3, that's the same thing as multiplying. Oops, multiplying by 3. So I'm going to add 1 to my exponent, which gives me 1/3, and then divide by 1/3. When I divide by 1/3, that's the same thing as multiplying by 3. So I'm going to put that 3 in front. So here's our anti-derived equation. It's not solved for g yet, but let's first figure out what that plus c is. And I'm given, here it is, this is my coordinate 0, 91. So that means t is 0 and 91 is g. So let me write that in. 91 minus 27 to the power of 1/3 equals, and then this would be 0 plus c, so I can just ignore that 0. All I did was I plugged this guy in to the equation. And so c is going to be equal to, c is equal to, so let's do this, 91 minus 27. Since this is a numerical expression, I'll just leave it like this actually. This is totally acceptable. Don't really need a calculator here. You can if you want and simplify it. C is going to be equal to 3 times 91 minus 27 to the power of 1/3. Now, I'm not going to box that. I'll just leave it. And I can rewrite that into my equation here. So let me now rewrite this nice and cleanly. So let me block this stuff off. Okay, so we're going to say that 3 times g minus 27 to the 1/3 is equal to negative t plus 3 times 91 minus 27 to the power of 1/3. There's my equation. I need to now solve it. Because in my next part, it's going to ask, based on this model, what is the internal temperature of the potato at time t equals 3? This equation is telling me what's the internal temperature of the potato at particular times. I plug in a time into here, it'll give me what the temperature is at that time. So let's go ahead and solve this guy out. So I'm going to isolate g, so g minus 27 to the 1/3 is equal to, and I'm dividing everything by 3, so negative t over 3 plus this 3 will cancel out. So I'll just have 91 minus 27 to the 1/3. Okay, if I have an exponent 1/3 here, then I need to, if I want to get rid of that 1/3, I will take the power of 3 on both sides. Take both sides to the power of 3. So that'll make this g minus 27 equals all of this, negative t to the power of 3 plus 91 minus 27 to the 1/3, all to the power of 3, all of that guy. And then I just need to add a 27 over to the other side, and that'll give me my equation. So g of t is equal to negative t over 3 plus 91 minus 27 to the 1/3 all to the power of 3 plus 27 out here. And it is asking us what is the internal temperature based on this at time t equals 3. So my last step now, let me block all of this off, I'll pick a new color, is to find g of 3. And since this is, it is acceptable to leave my answer as a numerical expression, unsimplified, take advantage of that. We're going to put negative 3 over 3 because I'm plugging in a 3 for t. So negative 3 over 3 plus 91 minus 27 to the 1/3 to the power of 3 plus 27. I can leave it like this because this answer is a numerical expression. I don't have anything else and no variables, no nothing else in there. It's all values, it's all numerical values. So I can leave my answer just like that, and that's perfectly acceptable. All right, here's an example with another particular solution, finding the particular solution to a differential equation. So I'll work this a little bit faster this time. And I'll separate my variables to start off. 1 over e to the y dy equals 3x squared minus 6x dx. Integrate both sides. Okay, so 1 over e to the y is e to the negative y. And whenever I antiderive anything with e in it, it's itself again, but then divided by the derivative of the exponent. So the derivative of negative y is negative 1. Then I got equals, antiderive all of these terms, so I got x cubed minus 3x squared plus c. I can rewrite this term over here, negative 1 over e to the y, x cubed minus 3x squared plus c. The coordinate I'm plugging in is 1, 0. 1, 0 is what I'm plugging in, so negative 1 e to the 0 equals 1 cubed minus 3 times 1 squared plus c. So this will tell me that c is equal to, so this entire thing right here, e to the 0 is 1, negative 1 divided by 1 is negative 1. And then I got 1 minus 3, so let me write this equation right here, negative 1 equals 1 minus 3 plus c, negative 2, negative 1. So c is going to be equal to positive 1. C is equal to positive 1. Negative 1 over e to the y is equal to x cubed minus 3x squared plus 1 now. Writing in my particular c value here. And now let's solve this for y. So now that I have an e in here, I might need to apply the natural log somewhere. But I'm going to have to first start by flipping this fraction, making it e to the y. So I flip this, and I'm going to multiply this negative 1 to the other side. So if I flip the left side, I have to flip the right side. So I got negative 1 up here, and then I'll put x cubed minus 3x squared plus 1 right here. Alright, so now how do I get rid of this e? Well, if you look on your study guide, e and natural log are inverses of each other. So to undo an e, I need to apply a natural log to it. So if I take the natural log of this, and I do the same to the other side, because whatever I do to one side, I have to do to the other side, natural log of e to the y leaves me just with y equals. So now I have this natural log here. Negative 1 over x cubed minus 3x squared plus 1. There you go. There's your particular solution. All right, last question. This is a BC only question. BC only. It is asking us to use Euler's method. So Euler's, I know this is a pretty straightforward topic, but Euler's method is only going to be on the BC's test. So if you're taking the AB test, you don't need to worry about Euler's. So you can stop the video here and you can go work on something else. I don't know. Or keep studying calculus. Anyways, so Euler's method involves this table, just like you see on your study guide. And we have to first figure out what is our starting point. So our starting point is this guy right here. H of 0 is equal to 2. And it even says starting at x equals 0. So 0, 2. I want to use Euler's method with 2 steps with approximating h of 1. So that means that I need to get from 0 to 1 using 2 steps, including the 1. So that means that I have to have a 0.5 in between here. Okay, I take my first step to 0.5, I take my second step to 1. That's 2 steps of equal size, and I'm approximating h of 1. I'm finding what is going to be this value, what's that guy right there going to be. Alright, so using Euler's method, I have y nu is going to be equal to dy dx x new minus x old plus y old. Alright, so I'm going to leave that general formula there so I can kind of write my values underneath there. So y new is always going to be the next y value that I'm looking for, and the old coordinates are what I already have. Okay, so I first need to figure out what dy dx is in this current step. So the way I do that is I plug in 0 and 2 into this equation here, the differential equation. So if I plug in a 0 for x and a 2 for y, I'm going to have negative 1 is my first dy dx, 0 squared minus 1/2 times 2. So I'm going to have y nu is equal to, and actually I'm not going to put y nu, I'm going to put f of 0.5 because I'm finding f of 0.5. That's the new y value. I'm going to have dy dx, so negative 1. Now I go x new minus x old, so 0.5 minus 0, plus the old y value, plus 2. So that gives me negative 1 times 0.5, which is negative 0.5 plus 2. So that gives me 1.5. So I'm going to put a 1.5 right here. And I'm now going to plug these two guys into here. Let's see. I need to be able to do this without a calculator. So let me do something here. This is question 4, so I'm kind of working without a calculator. 0.5 is the same thing as 1/2. This will make it easier for me to square something or multiply something if I have fractions. 1.5 is going to be the same thing as 3 over 2. 3/2. That makes it a little bit easier for me when I'm plugging in. Okay, you have to be able to do some of these things without a calculator to save yourself some time. Okay, so let's plug in this right here. I get a 1/4. And then 3/2 times 1/2 is 3/4. So I have 1/4 minus 3/4 is going to be negative 2/4. So negative 1/2 is my slope here. So now my next y-coordinate is f of 1 is equal to negative 1/2, the new slope. Then I have the difference between the x values, x new minus x old is still 1/2, so I'll put 0.5 minus, sorry, 1 minus 1.1 minus 1/2 right there. 1 minus 1/2, x new minus x old. And I need to add my previous y value, add 3/2. So I kind of switched in the middle to fractions because I realized I can't use my calculator in this question. Or, I mean, if you have your calculator, you can use it, but I'm just showing you how you would do this without one. Let's go ahead and simplify this guy. So I have negative 1/2 times 1/2, which is negative 1/4. Negative 1/4 plus 6/4. I'm converting this. Gives me a 5/4 here. And that's the guy that I'm looking for. So I'm approximating, and I know I wrote f, I should have written h actually, let me correct that. H of 0.5 and h of 1. So now I know h of 1 is approximately equal to 5/4. There you go, I used Euler's method to figure that out. As usual, if you have questions, please let me know. Email me, let me know. I'm going to be working on Unit 7 and 8 next. Unit 8 and 10 next. But yeah, if you have any questions, let me know.